Okay, so continuing on with lecture notes on exponential and logarithms for Math 112. This is a classic example of exponential functions, interest. So one major use of exponential functions is interest. Compound interest formula, A equals P, 1 times the quantity 1 plus R over M to the MT. A is how much you have in your account at time T in the future. P is how much you invested, called the principal, that's why it's P. R is your annual interest rate. It has to be a decimal in this formula. M is the number of times compounded, interest is compounded per year, and we'll talk about that a little bit later. And then T is the number of years. And note, your time always has to be in years. Be aware when my math lab uses something like months or weeks, right? You need to convert that to years. Okay, so why is an exponential? Time appears in the exponent. This is an exponential function of time. How much money is in your account goes up exponentially. So we'll do an example and then we'll talk a little bit about where that formula comes from. So Jane puts $1,000 into an account earning 6% annual interest compounded monthly in a half year, in 2 years, and 30 months. How much is in her account? So the 1,000, that's what she's investing. So that's her P. The interest rate is 6%, but we have to make sure that you do your interest rate as a decimal. So it's 0.06. M, how many times is interest compounded a year? It's compounded monthly. $12 times a year. So M is 12. If it was compounded weekly, then M would be 52. If it was compounded daily, M would be 365, what have you. And T, we're going to actually do 3 different times: a half year, 2 years, and then 30 months. That's 2.5 years, right? Because 24 months is 2 years, and then plus another 6 months, so 2.5 years. Always convert your time into years. So what's A? We don't know what that is. We have to figure that out. So what's my formula? We take this formula and plug everything in. You get A equals 1,000 times 1 plus 0.06 over 12, quantity to the 12t. There you go. And we can simplify that a little bit. 1.005 to the 12t. 0.06 divided by 12 is 0.005. 1 plus 0.005 is 1.005. So there's the formula for that. Keep in mind that you don't know what T is. And if you remember your order of operations, PEMDAS or BODMAS, exponentiation comes before multiplication. So you can't multiply the 1,000 in here because you haven't done the exponent yet. You have to figure out what the exponent is before you can do anything else. So set up a little table here. T, 1/2 to 2.5. And what's A? Well, you plug in T into that and see what you get. And if you do that, you'll find that after a half a year, she has $1,030.38, which makes sense. 6% interest, 6% annual interest. She should get about 6% of 1,000, which is about $60 over a course of a year. So in half a year, she gets about $30, a little bit more. After 2 years, she has 1127.16, and after 3 years, 1161.40. Now, on my calculator, here's my calculator. You do powers by using my power button. I use this, y to the x. You might have a caret, you know, a symbol for raising for power. That looks like this. On your calculator, and you can calculate these numbers like that. So where does this interest come from? Where does these formula come from? Well, compound interest works by taking what you got, multiplied by the interest rate as a decimal again, and adding that to what you have. So suppose you have $120 in the bank, and the bank compounds your money by 10%. That means they just calculate the interest. So how much do you have after the compounding? So you start with 120. Start $120. Interest, 0.10 times 120. Your interest rate is 10%. As a decimal, that's 0.1. So $12. Then you add 120 plus 12 equals 132. So that's how much money you have in the bank after interest has been compounded once. Okay. So what's going on here? We take 120 and we add 10% of it to 120. What's that equal to? Well, if I factor out the 120, it's that, or it's 120 times 1.1. I take 120 and multiply by 1.1, and that gives me how much money I have in the account after one time of interest being compounded, so $132. What happens if I do it 3 times? Well, $120, you get $12 in interest, 10% of 120, and then you add that, so that gives you 132. The next time they compound interest, they do it on the $132. 10% of that is $13.20. You add that to your interest, and you get 145.20. They compound interest again, so that means you start with 145.20, add 10% of that. 10% of that is 14.52. Add the 14.52 to the money you've already got, and that gives you 159.72. So what we've seen before is that the 132 from up here is 120, how much you started with, times 1.1. What's the 145.20? Well, that's the 132 you started with here. Same procedure, so it's just taking 132 and multiplying by 1.1. What's the 159.72? Well, we took the 145.20, added the interest. Adding the interest means just multiplying by 1.1. So we can backfill a little bit. 132, that's this. 1. Doing interest twice means you multiply by 1.1 twice. Doing interest 3 times, well, the 159.72 is 140.20 times 1.1, but 140.20 was 120 times 1.1 quantity squared, and then we multiply by another one, which is 1.1, and we get 120 times 1.1 cubed. 3 times you compound interest, you multiply by 1.1 3 times, which is 1.1 cubed. That was the other lecture. So, still doing interest. Here we go. So, how does our compound interest formula, which is A equals P times 1 plus R over M to the MT. If your interest has been compounded n times, after n compounding periods, it means your interest has been compounded n times. The amount that you have in the account is 1.1. A equals 120 times 1.1 to the n. Okay. It was 3 times of 120 times 1.1 cubed. Okay, so this is your principal. The 1.1, well, that was 1 plus your interest rate. The per period interest rate, how much interest do you get each time period is R over M. So if we go back to the previous example with Jane, right, she gets 6% interest compounded monthly. So that means every month she gets 0.5% interest, right? So 6% interest spread over 12 months, 6 divided by 12 is half. So you get 0.5% each month, that's the 0.005. So P equals 1 plus R over M to the N. N is the number of times it's been compounded. M times a year. M is how many times it's compounded, times T, which is the number of years. That gives you how many total times it's compounded. If you compound interest for monthly, 12 times a year for 10 years, that'd be 120 compounding periods. And so there's the formula. So one of the questions that comes up is if you make M, this term, bigger and bigger and bigger and bigger, right? If you compound money faster and faster and faster, how much interest do you get? So we'll do a mathematical experiment because you never get 100% interest. But suppose you had $1 that was invested at 100% interest. So what compounding rate would give you the most money in the account at the end of 1 year? And how much would you have? So yearly, compounding period 1 year, that's $2. So yearly, that means you start with $1, you get interest of $1 because it's 100% interest. At the end of the year, you have $2. Semi-annually, that means 2 times a year. Right, so that would be in June and December, I guess. So you start with $1, you get 50 cents in June, and that gives you $1.50. Why do you get that? Well, if you're getting 100% interest twice, that means you're getting 50% interest in June and then another 50% interest in December. So in December, you have $1.50 in your account. Half of that is 75 cents, so you end up with $2.25 in your account at the end of 1 year. So compounding, you get less interest per period, but you get more periods, and so you end up with more interest at the end of the year. And if you keep doing that, you can do quarterly is 4, monthly is 12, weekly is 52, daily, hourly, every minute, every second, et cetera, et cetera. What happens, the amount of money that you get, it builds up, but it reaches a limit. It reaches this limit, and this limit is a number called E, right? If you have infinite amount of compounding periods, if you're compounding all the time, E is 2.718, 281828. And it's a number. That's what that number E is. And there's a formal definition. If you take calculus, you'll see that formal definition. We're not actually going to do it. So the compounding interest formula, when you're compounding all the time, that's called continuously compounded interest, is A equals P e to the RT. A and P, those are still the same. This is what you invest. This is what you have in the future. R is your interest rate as a decimal. And T is the number of years. E, this thing here, the base of your exponential function, that's just this number. And your calculator should know that. Here's my calculator again. And if you look here, there's an e to the x. There's a button that says ln, and then above that is e to the x. So if I turn my calculator on, hopefully you can see that. If I put in 1 second function e to the x, it gives me e 2.71828. So your calculator knows what E is. You don't need to remember it. Great. So suppose Ben Franklin invests 1 cent in 1750 at 4% interest compounded continuously. How much is it worth in 2020? Compounded continuously means we have that formula. So A, P, R, T, what are those in this? How much you invest, 1 cent, so 0.01 because that's 1/100th of a dollar. Interest rate is 0.04 because remember that has to be a decimal. Time, well, he invested it in 1750, it's now 2020. So 250 years, 270 years. Time is always in years. Years. Great. So how much does he have? Question mark. Well, the amount that he has is 0.01 e to the 0.04 times 270. Put those in parentheses in the exponent. And then we can get an answer of $490.21. And so that's how much he has in the account. And so that's an example of compounding continuously and its formula. There's two types of compound interest: compounded continuously, which is this formula, and the other piece of paper, there it is, compound interest, which is that formula. Okay. Now, one of the questions that always comes up in dealing with finances is how long, right? And we can use the intermediate value theorem to get approximate answers to this. And we saw the intermediate value theorem back in chapter 2. But logarithms allow us to find the exact answers. So suppose Jane needs $600 to buy a bike, but she only has $400. And she has a bank that gives her 6% interest compounded continuously. So how long to 2 decimal places will take her money to grow to $600? So continuous compounding, that's A equals P e to the RT. Oops, there we go. Continuous compounding, A equals P e to the RT. A is 400, e to the 0.06 t. So there's our function. And we know what this graph should look like. Right? It's an exponential function. We have to be a little bit careful about what our points are here, because this graph is now being multiplied by 400. It's being stretched away from the x-axis by a factor of 400. So if t equals 0, a equals 400 times 1. So this goes through 400. And if t equals 1, a equals 400 times e to the 0.06, which is some number. But the graph looks more or less like that. But you do have to be careful when you're multiplying it by a constant, because that stretches the function up. So anyway, this is a little bit of the graph. It's been scaled in a weird way, because if you notice, the numbers on the y-axis are hundreds: 200, 400, 600, 800, and then the years: 0, 2, 4, 6, 8, 10. So this is dollars. This is the amount. We want to know, when does a graph get to $600? And it's somewhere between 6 years and 7 years. And so you can plug that into your formula down here and see what the amount is in the account. After 6 years, she has $573.33. After 7 years, $608.78. So what that means is the graph goes through the line 600, where the x value is somewhere between 6 and 7. And you can narrow it down a little bit, and this is what the intermediate value theorem is, really. Between 6.7 and 6.8, at 6.7, she has $597, and I can't read my handwriting, but I think that's 12 cents. And after 6.8 years, she has 601.53. So somewhere between 6.7 and 6.8 years, she hits 600 exactly. So you can narrow it down a little bit further. And it's somewhere between 6.75 and 6.76 years. So 6 3/4 years will take for money to go from 400 to 600. This is approximate. We want to be able to find the exact answer, and logarithms is the tool that lets us answer these sorts of questions. Okay, so we'll start with that in a second.